Hello friend, my name is Pravesh Chauhan and welcome back to my YouTube channel International Academy of Physics. Thanks for your love and kind support and to subscribe my channel. So today again I have very interesting topic for you, that is how to apply Kirchhoff's laws to find the current in the complex circuits. So I heard many students are facing problems in solving these complex circuits with the help of these laws, Kirchhoff's laws. Even some students don't know how to apply Kirchhoff's laws and what is the correct way to apply these rules. So first of all, you should know the difference between simple electric circuit and the complex electric circuit. For that, let's go to the lab. Okay friends, let's see the difference between simple and complex circuit. So there are the two resistors of values 10 ohm each, and if I connect with these two resistors with a battery, okay, through the connecting wire, let's do the connection in that way. Okay, this resistor is connected with that one. I will take one more connecting wire, I will connect to the battery negative terminal, and this switch I will connect here, and I need one more connecting wire that I will take it this one and I will join with this switch, other end of this switch. Okay. So now, alright, perfect. So now what actually is it? This is the circuit of two resistors. Okay, the battery resistors. It could be like your electric bulb or anything. Even you can change this with the bulb. So this one is the simple circuit, and you can check there is only one loop. You can check it here. Okay, there is a one loop. Now if I switch on this circuit, now circuit is closed and the electrons are moving. So right now we can check the direction of current. As you know, it's conventional direction. Okay, the direction of the current would be opposite to the electrons here. Now that is the simple circuit. The question is, if you have to calculate the current, okay, if you have to calculate the current which is flowing through the circuit, so how will you do this? How will you solve? So simply you can use the Ohm's law, right? So by using Ohm's law, that is V is equals to IR. Current you have to calculate. V is the 9 volt here battery, and the resistance. What is the effective resistance of this circuit? So these both resistors, as the current is same across this one, so these resistors are connected in series. So the effective resistance of this circuit is 10 plus 10, it's a 20 ohm. So resistance is 20 ohm, potential difference, or you can say the battery potential is 9 volt. So the current will flow through it I is equals to V over R. That means 9 volt divided by 20 ohm. So 9 over 20, it would be 0.45 ampere. So that is the current here. So you can check it here, what current is flowing through it. Okay, at any point you can check, and that would be, you can check this value 0.45 ampere. Okay, at any point you can check, the value remains same because the current remains exactly same. Okay, one more important point here. If you want to check the potential difference across these resistors, okay, as you have studied in your lower classes, so if the resistors are connected in series, so the potential, that effective potential difference of this battery, this 9 volt, or if you neglect the internal resistance of the battery, so this EMF would drop equally across 10 ohm resistor and this 10 ohm resistance, right? So this one is the 9 volt. So if you check the potential difference across this resistance, so you will get it here 4.5 volt. So net total potential is 9 volt. So 4.5 volt here, and here also you can check it if you want to check over there across this terminal, these two terminals. So that would be the same exactly. Okay, just ignore that the sign over there. Okay, we can change these one, right? So 4.5 volt and 4.5 volt, so net would be the 9 volt. So what actually, okay, you got the concept over here. So net electric potential would be equals to this one. So that means whatever the potential dropped here,
or you can say the loss of potential across these two resistors. So sum of these two potential drop would be equals to that one. So you will study in Kirchhoff's loop rule, okay, the net EMF or algebraic sum of the EMF of the loop would be 0. That means whatever the EMF of this battery, it is dropped across these resistors here. So IR and IR, you learn it there. I will be back after solving one question based on the Kirchhoff's rule, right? So the question is, this is the simple circuit, and if you want to make it the complex, okay, how can you convert this circuit as a complex? So complex circuit is what? Where you have more than one loop, or more than one battery. Okay, so basically you can make one or two more loops to make it complex. Okay, so battery doesn't matter, even a single loop you can add 2-3 batteries here. Okay, so it doesn't like the net EMF that you have to calculate what would be the effective potential difference across the terminals, right? So let's make it complex. Okay, let's join one more battery. Okay, so this time let's convert, just reverse this terminal over here. Okay, and one more resistance, we can take it across this end. All right, here we can connect one resistor across this one. Okay, and that one. All right. Okay, so let's connect one switch and another wire here, connecting wire. All right, yeah, got it. So how many loops are there? 2 loops. Now still the question is, the current is flowing in that first loop here because switch is closed over there. Okay, that circuit is closed, right? But this loop is open. You can say the switch, if you switch on it, then the current will flow across this one. Okay, now the question is, if you change some resistances over there, okay, then there would be difference in the current across this one. Okay, let's make this little high resistance, so you can see there is a current flowing in all these branches here. All right, so this resistance is 39 ohm. Here also you can reduce little bit that resistance. Okay, so now there are the 2 loops here. Now question is, if you want to solve what current is flowing in which branch, so that to solve these currents you have to use Kirchhoff's rules. Okay, how many currents are there? Okay, now look at that. At every point you will get the different current here. Across this branch the current is 0.31, and across this side the current is 0.32, and across this one the current is 0.63. Okay, one more important point which we will use in the Kirchhoff's rule is what? These points are called junction. Means where the currents are enter the point, okay, that point where the currents are entering or the leaving, right? So that these points are called junction. So you have 2 junctions here, this point and that point. So at this first point, one current is entering from the top and 2 currents are leaving here. Okay, at this point 2 currents are entering and 1 current is leaving. Okay, so that is the Kirchhoff's first rule that we will discuss next to this slide. Okay, so whatever the amount of current enter here, so these are divided, this current will divide in this form, right? These 2 branches here. So the sum of these 2 current would be equals to that one. So if you check it here, the current is 0.63. Okay, and this branch the current is 0.32 and this is 0.31. If you add these 2, it becomes 0.63. Alright, in the same way here this current is 0.63, that means here across these 3 parts the current is same, 0.63, 0.63, but here the current is different because there is a different register here. Alright, so there are 3 different currents. You can take this as I1, this is I2 and this one is I3. So in Kirchhoff's that one, in the complex circuit in exams they ask about these three currents. So you have to calculate I1, I2 and I3 by using Kirchhoff's rule. So in exams we don't use these lab works or these virtual labs. So there we have to write we have to solve these currents I1, I2, I3. So what we do, let's take one question, okay, in the similar of two loops, and we will solve the currents for all. Let's take three currents, right, in that question, and when you got all these three currents, then we can check it whether our currents are correct or not. Okay, so let's go back to the slides and solve one question, and then we will verify that question again in that virtual lab here. All right, okay, so back to the question here. Okay friends, let's take one example, or we can solve one question using Kirchhoff's laws. So in this circuit diagram, or you can say the complex circuit, okay, three different resistors, one 5 ohm, 10 ohm and 20 ohm, they are connected across two different loops. In one loop the battery is 12 volt and the second one is the 6 volt battery. There are the three currents in this these both the loops. One is on the first loop, it's a current I1, this arm it's a current I2, and this is current I3. So these are the currents which we have to solve. Okay, we have to find the values of I1, I2 and I3. So Kirchhoff's laws will help us to calculate these values. Now before using these laws, let's have a look on this. What actually the Kirchhoff's laws, right? So Kirchhoff's laws and some sign conventions. Okay, now you know in all the circuits, when you connect in Ohms using Ohm's law, a battery is connected with the different resistors. Okay, so just we normally draw the direction of current from positive terminal to the negative one. Potential at that point A and point B would be different here. Let's say if the potential is 6 volt here, so at point A you can say it's a 0 volt and here it's a 6 volt, right? So simply what happened, it's a from A to B the potential increases, and if you can say the positive to negative, the potential decreases here, right? So that you have to keep in your mind. So if you have a battery, you just assume that the energy increases, or you can say the potential increases negative to positive. So you can draw these directions for the battery. Okay, that is the increasing potential order. You can take this as a fixed, okay, for the battery. It doesn't matter what current is flowing in the circuit, but you can check it here. This battery, the potential increases from negative to positive, that one. So this will help you to find the clear sign of that potential drop. So you can use that one. From A to B the potential increases by E. E is the EMF here, and from B to A the potential decreases, right? So Kirchhoff's, there are the two laws here. The first one is the sum of the current entering a junction is equals to sum of the currents leaving that junction. I already told you in this previous virtual lab. So the junction, at one particular junction some currents are entering, some are leaving. So this first law is basically based on that about the current, right? So for that you can write this rule in that way, a junction rule. So sum of current which enter to the junction would be equals to the sum of all the currents which are leaving. Okay, for example, if at this one is the junction here, okay, and there is a one current, one arm is entering here, the current, let's say this one is the 10 ampere current is entering, and from the junction two currents are leaving, or two resistors, these are two different resistors are there, okay, and this arm also one resistor. So across one end the 10 ampere is the current is entering to the junction. So how much it would be there? These are these two. Okay, let's say that current is if this current is 6 ampere, right, then this would be the 4 ampere. Now how much? It depends on their resistance, what resistance are there in the branch here. So sum of these two would be equals to that one. So 6 plus 4 would be equals to 10. So sum of the current enter, only one branch is there, so 10 ampere, leaving
there are the two wires over here, two resistor there, so you can add these two currents, 6 plus 4. So that is the first law, that is called junction rule. Okay, so Kirchhoff's second law, the sum of the EMF around any closed loop must equal to the sum of the IR drop around that same loop, right? So what does it mean? This total EMF across that loop would be equals to total potential drop in the same loop. Okay, if you have multiple resistors are connected, as I have already shown to you, okay, and different batteries are there connected across this one, right? So let's say this resistance is R1, this is R2, and let's say the current across this is flowing here, it's a I, okay, because it's a single loop, only one current is flowing through it, the same as you can use it here, right? So this is the potential, let's say this is E1 electric potential, this one is E2, V1 or V2, you can write it here. So what does it mean? So summation of this one, the net potential difference across these batteries here, so you can write it E1 and E2, okay. If you look at that one, negative to positive, they are increasing same order, it's written here, so simply you write E1 plus E2, that would be equals to IR. So how many resistors are there? R1 and R2. So current is same, so you can say, and the current this IR1 and IR2. Now the question is, what should be the sign over here? Okay, so sign convention you have to follow like this one for the batteries, for the EMF. Okay, look that one, I have already drawn these symbols here. A to B the potential increases here, right, and B to A the potential decreases simply. So right now you can keep this sign with the same negative to positive here. What is the red line? This red line is your tracing direction. Tracing means you have to choose your tracing cycle, whether you are following the loop clockwise or anti-clockwise. So that is this red line. So if your tracing direction is same as your battery, this one, the potential sign, or you can say the current over here, then you can take this one as a positive. So this EMF you have to take as a positive. But if your tracing direction is opposite to your battery, this one traced the current, then you have to use its negative one. Okay, so simply this arrow is same on both the pictures here, only direction is this changes here. So if they are parallel, take positive, if they are opposite, take negative, that's it. Okay, EMF. So what is the sign convention for the sign for potential drop or IR across the resistors? So simply again same you can follow. If the current, let's say this is the direction of current across this resistor and this is your tracing direction, if tracing direction and current is same, so take is positive, if they are opposite, take is negative, that's it. Okay, alright, so A to B IR drop is positive and B to A this IR drop is negative. Alright, okay friend, let's solve one complex circuit using Kirchhoff's laws, right? So on the right side you can see this this circuit, it's a complex circuit here. So we can use Kirchhoff's rules to solve this problem, right? So first of all you have to check the direction of current is given in the circuit. Okay, the values of resistors and the potential battery is given here. There are two batteries in this circuit, 12 volt battery and this one is a 6 volt battery, and three currents are there. I1 that's flowing in the loop 1 on that side across this 5 ohm resistance, and I2 is flowing across this 10 ohm resistor, and I3 is flowing in this set, right, across this 120 ohm resistor, right. So if we take the loop, we'll start with the loop 1, and before that we can use the junction rule. Okay, so as per the junction rule, where is the junction? Let's that point, it's a B, yeah, that point is C here. At the point C, look at that, this one I1 current is entering to this point junction, and these are the two currents which are leaving the junction, I2 and I3. Okay, so now
as per the junction rule, we have this relation I1 would be equals to I2 plus I3 as shown in this diagram, and now we have to select a loop 1, okay, to follow the rule number 2, that is the voltage rule. So across this loop 1 we have to choose our tracing direction. Okay, that's it's your choice whether you choose this clockwise or anti-clockwise. So the red line, this is our tracing direction. So I will take positive values along these directions, and yeah, let's check it here. So to apply the voltage rule, I will follow this rule here as we have already discussed. Okay, E would be equals to IR. So sigma means the total net EMF across this loop. So if take the loop 1, so how many batteries are there? It's only one battery, so I will write the equation. Okay, for the loop 1 I will write the equation is 12 volt, that would be equals to IR, the sum of all these IR. So we have two resistors, one is 10 ohm resistor, the current is I2, so potential drop across the 10 ohm resistor is 10 I2. Okay, and this is positive. Why? Because my loop direction is clockwise, like tracing direction is clockwise, and direction of current across 10 ohm resistor is also clockwise, so that I will take it's positive, right? And then that second resistor is 5 ohm, and 5 ohm resistor I1 current is there, and the tracing direction and the direction of current I1 is same, so we will take this as a positive, that is 5 I1. Okay, so that would be the equation number 1 for the loop first case here, right? Loop number 1. So that is the loop 1. Now for loop 2, that one more equations you can write for loop 2. Okay, let me change the color, is the yellow one. So in the loop 2, we can check it, we can take the directions clockwise again in the loop 2. Okay, so if we take the tracing direction clockwise, so again we can write here. Okay, let me draw the line over there. So for loop 2, we can check it here, just a minute one. All right, now color. So what is the potential here? That is the 6 volt, and the potential drop is we have 20, and what is the current across this 20 ohm resistor? That is I3. So it is 20 I3, and check the sign whether it's positive or negative. Look at that one, tracing direction is clockwise, and the direction of current I3 is also here clockwise, so both are positive. We have to take the positive one. And now the another resistor is 10 ohm resistor. So our tracing direction is clockwise, right? But the direction of current across this resistor is opposite to our tracing direction, so that value you will take -1. So it is minus 10 I2. So that is for the loop number 2 equation. Now we have to solve these. We have right now 3 equations. Okay, one as on the basis of junction rule, second equation we have taken from the loop 1, and this equation we have to we have already solved this for loop number 2. Okay, now let's simplify this part. So what we do, we can look at that one, this equation, that equation is in terms of I2 and I1, and this is I3 and I2. So what we can do, we can replace this I1, okay, by using this value I2 and I3 from where? In this equation. Let's assume that equation number 1, and this is equation number 2. So equation 1, in equation 1 I1 it can be replaced, so it becomes 12, that is equals to 10 I2, okay, and plus 5 I1. I1 can be written as I2 plus I3, so we can write it here 5 I2 plus 5 I3. Okay, now if you can simplify this one, 10 I2 plus 5 I2, it becomes 15 I2. Okay, 15 I2 and plus 5 I3. Alright, that is equals to 12. This equation you can mark as 3. So right now you have 3 equations, right? So we have to solve for I1, I2 and I3. These currents we have to calculate. Now equation number 3 and equation number 2, you can check it here. Both are in terms of I3 and I2. So one current we can eliminate. So let's eliminate I3 current, right? So here it's a 5I3, this one is 20I3. So what do we do? We can multiply equation number 3 by, okay, let me select one color again. So equation number 3 we can multiply, by what number we should multiply? You can multiply by 4. So when you multiply this by 4, it becomes 48. That would be equals to 15, 4 times how much? 60 I2 and plus 20 I3. Okay, so now this equation, yellow one, and that equation number 2, these we can simplify that one. So you can take this as equation number 4. So what we do? We can subtract equation number 4 minus equation number 2. Alright, so we can write it again. So 48, let me take the color here. So this says now 48 is equals to 60 I2 plus 20 I3, and that equation we can write it again. It is 6, this is 48. Okay, 6 is equals to 20 I3, I will write it here, 20 I3, and plus that is negative 10 I2, so minus 10 I2. Okay, we can subtract it. So when you subtract, the sign will change. Okay, it becomes negative, this one is become positive, this become negative. So plus minus, that would be cancel out. So 48 minus 6, it is 42. That would be equals to, now here it's 60 I2 and plus 10 I2, it becomes 70. Okay, that is 70 I2. So from here you can calculate I2. So how much? I2 is becomes 42 divided by 70, and hopefully if you do this calculation, so I2 would be equals to 0.6 ampere. So now I2, we got the I2 here. Now we have to calculate other two currents, okay, I1 and I3. So for that we can use equation number 1. Okay, so use equation number 1 to calculate, in equation number 1 we can calculate I1 here. So from that equation, okay, we can calculate I1. So we can write it again. 12 is equals to 10 times 0.6 plus 5 I1, and you got it here, right? So 12 is equals to, how much is it? It becomes 6, right? 6 plus 5 I1. So now what that? So 12 minus 6, it's 6 here, and 5 I1. So that means I1 would be equals to 6 divided by 5, and that is 2, right? 1.2 ampere. So I1 is also, we got the I2 here 0.6. Okay, I1 we got it here 1.2 ampere. Now this says I1, yes. So I1 and I2, now you can substitute the value here in the junction rule. So I2 plus I3, right? I2 plus I3, that is equals to I1, and I1 is what? 1.2 ampere. So I2 is also, okay, sorry, I2 plus I3, this is I3 here. I2 value is 0.6, 0.6 you can write it here, and plus I3, that is 1.2 ampere. Now I3 you can calculate easily here. Now 1.6 minus, 1.2 minus 0.6, so you will get it 0.6 ampere. Okay, so I3 is also
0.6 ampere. Now these are the values which we got by using these laws, right? We have already calculated. So I1 is 1.2, that means this current is 1.2, okay, and the I2 and I3, these values, so that is 1.2 ampere, I1 and I2 is 0.6, and this one is also 0.6, right? So to know whether these are correct, although in this in the loop circuit it shows that it should be correct, right? But we can verify with the some again we can check these values in the laboratory there in the virtual lab. So let's check. If we connect these resistors of the same values 5 ohm, 10 ohm, 20 ohm with these two batteries 12 volt and 6 volt, let's check whether we get the same current or not. So let's go to the virtual lab, right? Alright, so I hope you remember what current we have calculated in that question. So our current was I1 was 1.2 ampere, I2 and I3 was 0.6 ampere. So let's set the same circuit and check it whether it's correct or not. So we have three resistors, right? So one resistor was in loop 1, second was there in the other branch of loop 1 and 2 common branch, right? And the third resistor was here like this. Yeah, I remember that circuit. Let's say that one is over here. Okay, now there are the two batteries. One battery is in that loop 1 and another battery is here. Okay, so we can change here direction because the positive terminal was downward. Okay, and let's okay, so better we change this symbolic form, right? This one is quite okay. Now what we do, let's connect all these circuits with the help of connecting wire. One is connected with this part, another one is connected with that connecting wire, and here one is okay connected with this. So here we can, alright, we can do what the thing here. Anyway, no problem, we can take one more wire over there, right? So let me join this part. Oh, current started from there because that battery, that's a one single loop is connected here. But we can, okay, let me just cut this part and take one more connecting wire. Okay, just a minute. So direct I can connect with this one right here, and this one we can have one more connecting wire over here like this part, right? Now the question is, that was the circuit hopefully, and one more thing, this terminal, this battery was in that order, right? So that resistance value was 5 ohm. Okay, we can mark it's a 5. Okay, this one is a 5 ohm. Okay, let me check it here as per the circuit diagram, right? This battery volt is the 12. Okay, and that resistance is 10 ohm, 510. This resistance should be 20 ohm. Okay, let's take this one as a 20 ohm. All right, okay, so that's 20 ohm, and this battery voltage was 6 volt. If you check the circuit, okay, it was 6 volt battery. All right, so these are the direction of electrons, right, moving. So let me check it here. We can show the direction of current, that is conventionally opposite to the direction of electrons here. Now all values, if you check the values are written here. 5 ohm resistance, this one is 10 ohm, this is 6 volt battery, here is the 20 ohm resistance, 12 volt, right? So that was the circuit which we have already solved in the previous section. So now let's check what are the currents. So that upper one, loop 1, we consider that current was I1. So I1 current enter into the junction point C. So I2 and I3 they are leaving. So what we have calculated, I2 and I3 as per our calculation, that was 0.6 both, and this I1 was 1.2. So you can check it here whether our calculation was correct. So first of all, let's check I2. So I2, look that one, the ammeter shows the current is 0.6 I2, and this one is the I3. Here we can check it here, I3 is also 0.6. If I2 and I3 are 0.6, 0.6, okay, and that would be the 1.2, because this I1 is the sum of I2 and I3. That means our calculation is correct. Okay, yeah. And one more thing here, if in this circuit they have given direction of current, if by chance direction of current is not given, you can choose your own direction of current, but follow the rules carefully, right? If you are applying Kirchhoff's loop rule in the loop 1 and loop 2, like in loop 1 if you are doing clockwise, okay, you do some calculations clockwise, so don't change this, okay, by yourself, right? Like this, some part you did the clockwise and other part is anti-clockwise, so then you'll get the wrong answers, right? So that was the verification of your result, and hope you enjoy that one. So that's it for today. If you like this video, please don't forget to subscribe and like. That's it for today. Thank you.